So, back in 1911, Albert Einstein puts out this paper, and it's a game changer. Now, this isn't his big, famous theory of general relativity, not yet. Think of this as, well, a preview. It was smaller, yeah, more focused, but honestly, maybe even more gutsy. It was just one single prediction you could actually go out and test, and the whole thing kicked off with a simple thought experiment. And when you read what he predicted, the sheer audacity of it is just incredible. He's basically saying, hey, you know that giant star we orbit? Its gravity can literally bend a beam of light from a star millions of miles away. And this wasn't some wild guess he just pulled out of thin air. No, it was the logical, unavoidable conclusion of one of the most elegant thought experiments in history. He even did the math and calculated the exact amount it would bend. Okay, so first things first, why was Einstein even bothering with this? He actually says in the paper that his earlier work on the subject just didn't sit right with him. He felt like something was missing, you know? A piece of the puzzle was gone when it came to gravity. But the really big deal here was that he finally saw a way to take these abstract ideas out of his head and put them on trial in the real world.
And where does he start? With something so basic we never even think about it. You know the classic experiment, right? A feather and a bowling ball, in a vacuum, they fall at the exact same speed. Einstein looked at that and thought, wait a second, this is one of the most universal things in nature, and yet it has no real place in our fundamental theories of physics. He figured this couldn't be a coincidence. No, this had to be the clue, the key to unlocking the whole mystery of gravity.
And following that clue led him to what he famously called the happiest thought of his life. It's one of those ideas that's so simple on the surface, but so incredibly deep underneath. This one thought would become the absolute foundation for his entire new theory of gravity.
All right, so let's try it. Imagine you're standing in a windowless box, like an elevator, here on Earth. You drop a ball, it hits the floor. Simple. You feel your own weight, right? Now, picture this. You're in the exact same box, but you're in deep space, far away from any planets. But this box is being pulled by a rocket, so it's accelerating upwards. You let go of the ball. What happens? Well, the floor rushes up and meets it. From your perspective inside the box, it looks exactly like it's falling. You even feel that same pressure on your feet. There is absolutely no experiment you can do inside that box to tell the two situations apart. They are identical. And here is the genius move. Einstein says, what if these two scenarios aren't just similar? What if they are physically, fundamentally the same thing? That's it. That's the principle of equivalence. And man, what a game changer. For hundreds of years, gravity was this weird, spooky force acting at a distance. But with this principle, Einstein gives us a key. He's saying we can forget the mystery of gravity for a minute and just study something we understand really well, acceleration. And whatever we learn there, well, it has to apply to gravity too. Now, once you accept that principle, that gravity and acceleration are two sides of the same coin, things start to get weird, fast. It's like a chain reaction of bizarre and totally unavoidable consequences. And the very first domino to fall, it has to do with energy itself. So we all know the famous equation, right? E equals mc squared. At its core, it tells us that energy has what's called inertial mass. Basically, it has heft. It resists being pushed. But Einstein, he's never satisfied, so he asks the next logical question. Okay, if energy has inertial mass, does it also have gravitational mass? Or to put it simply, does energy have weight? Does gravity pull on a beam of light the same way it pulls on a rock? Let's go back to that accelerating box in space to see how he figured this out. Okay, imagine we shoot a little pulse of light from the ceiling down to the floor. Now, it happens super fast, but in that tiny fraction of a second, the box is still accelerating, so it speeds up just a little bit. That means the floor is actually moving towards the light when it hits. It's just like when an ambulance siren sounds higher pitched as it races towards you. That's the Doppler effect. The same thing happens with the light. It arrives at the floor with a little bit more energy than it started with. And here's the kicker. Because of the principle of equivalence, if this happens in our accelerating box, it has to happen in a gravitational field on Earth too.
So you have to ask, where did that extra energy come from? The laws of physics are pretty clear. You can't just create energy out of thin air. Einstein realized there was only one possible source. It had to come from potential energy, just like when a ball falls off a shelf and picks up speed. And the only way something can have potential energy in a gravitational field is if it has gravitational mass. And there it is. The absolutely mind-blowing conclusion, energy itself has weight.
But believe it or not,
It gets even weirder. That same simple thought experiment about a box and a beam of light, it leads to an even more profound conclusion, a conclusion that completely messes with our understanding of time itself.
Okay, stay with me here. The energy of a light wave is tied directly to its frequency. You know, how many wave crests pass by every second. So if we already established that our light pulse gains energy as it falls in a gravity field, that must mean its frequency goes up too. It literally arrives at the floor with more waves per second than it had when it left the ceiling. Just think about that for a second. That sounds completely impossible, right? It's like me sending 10 text messages in a minute, but your phone says it's receiving 11. How does that work? Where did the extra one come from? Where are these extra light waves being generated? Einstein's answer to this paradox is just, well, it's breathtaking. He says the number of waves doesn't actually change. The problem is our assumption that a second means the same thing for the person at the ceiling and the person at the floor. He realized the only way this makes sense is if clocks tick at different rates depending on how strong gravity is. A clock closer to Earth, in stronger gravity, literally ticks slower than a clock further away. Gravity doesn't just pull on things, it warps the very fabric of time.
And again, this isn't just some philosophical mumbo-jumbo. It leads to another prediction you can actually test. If light falling into gravity gains energy, then light climbing out of a strong gravity field, like the sun's, must lose energy. It's like throwing a ball up in the air. It slows down. For light, losing energy means its frequency drops, which shifts its color just a tiny bit towards the red end of the spectrum. This is a real, measurable effect we now call gravitational redshift.
Okay, so let's put all the pieces together. We have the principle of equivalence, we have the idea that energy has weight, and we have the fact that gravity warps time. When you combine all of that, you arrive at the paper's grand finale, the real showstopper, the prediction that light itself must bend when it passes a massive object like the sun. Think about it. How do you measure speed? It's distance divided by time. But we just established that gravity messes with time. If clocks in stronger gravity tick slower, then if you're using one of those clocks to measure the speed of light, you're going to get a different answer. From the perspective of an observer deep inside a gravity well, where time is chugging along slowly, the speed of light would actually appear to be slower than for someone far away in space.
And that's the final piece of the puzzle. Picture a big, flat wave of starlight coming from a distant star, and it's about to graze past the sun. The part of the wave that's closer to the sun is in a stronger gravitational field. So, according to our logic, that edge of the wave is traveling slower. The other edge, farther away from the sun, is traveling faster. So what happens when one side of a wave moves slower than the other? The whole thing has to turn. It pivots. The light ray bends around the sun.
And of course, being Einstein, he didn't just say, hey, it probably bends. He did the math. He calculated the exact amount. For a beam of starlight just skimming the surface of the sun, he predicted it would be deflected by 0.83 arcseconds. Now, that is a tiny, tiny angle. To give you an idea, it's about the thickness of a single human hair seen from over 60 feet away. So, yeah, minuscule. But the claim itself, absolutely monumental.
And with that one specific number, Einstein basically threw down a challenge to the entire scientific world. This whole crazy line of thinking, which all started with a guy in a box, had ended up with a concrete, measurable number. Something that astronomers could actually go out and try to prove or disprove.
But there's a pretty big practical problem, right? How on earth do you see a tiny star that's right next to the blindingly bright sun? You can't. It's totally impossible. Most of the time. The only way you could ever do it is during those few precious minutes of a total solar eclipse, when the moon slides in front of the sun and everything goes dark, allowing those nearby stars to pop into view. And that's pretty much how Einstein wraps up the paper. There's no big triumphant declaration. Instead, it's this incredibly humble, almost urgent request to the astronomers of the world. He flat out admits his ideas might seem insufficiently established or even bizarre, but he begs them to go out and check. He was literally betting this entire revolutionary idea on what they could capture in a single photograph during an eclipse.
It's just such an incredible story of pure logic, isn't it? Every step flows from the last, leading to a conclusion that's more world-changing than the one before it. And to think it all started with an observation we all take for granted and a simple thought experiment. It really makes you wonder, doesn't it? What other profound truths about our universe are just sitting there, hidden inside a simple thought, waiting for someone to think it.